Hi everyone, in today's video we will delve into the concept of train test split and discuss it in detail. We will explore how to effectively apply this concept when training the model and then utilize the trained model to evaluate its performance on unseen data from a test set. To illustrate this, let's consider an example with 100 labeled observations, just like this. So over here we have 100 observations. As you can see, we consider a subset of 10 features, which is very small as compared to the real world data standards. Just for the convenience sake of understanding the train test split problem, we consider 10 features, and then we have a set of target variables y1 till y100. Now if I consider the part 1 of the video where we were talking about a regression problem, all the yi's are going to be on a continuous scale. But in case we are considering a classification problem, which we've discussed in the part 2 of the video series, it is going to be discrete. The target is going to be discrete. Now, in the previous videos, we use the complete data to train the model, which will mean that the entirety of 100 observations are being used to train the model uh, and estimate the parameters, which were like W1, W2, B, and so on. However, in real life scenarios, it's common practice to reserve only a portion of the available data for training, typically around 80%, and the remaining observations are then utilized to validate and assess the model performance. So, in short, we do something like this. So we say that the first 80 observations or any randomly selected 80 observations are going to be used for training tasks, and the remaining 20 observations are going to be used for testing. Now we will explain what this train and test means. The first and foremost thing which needs to be considered over here is the fact that the 80% of the observations uh, are selected randomly. It doesn't need to be in a sequential order. These are some 80 randomly selected observations which we are using for training our model. And by training our model, we mean estimating the parameters of the model. The test set is a set which the model hasn't seen in the training phase at all. By applying the trained model to this independent test set, we can assess its ability to generalize and make accurate predictions on new unseen observations. This evaluation helps us to estimate the model's performance on the real world data, which is actually unseen, and validate its effectiveness in making reliable predictions. The train test split technique is a very important component in any machine learning models, or in fact any deep learning models which we will be using, as it allows us to measure the model's performance in a controlled manner before deploying it in production. It helps us identify any issues such as overfitting, where the model is going to memorize the trained data but performs poorly on a new data, which will happen when you see that the performance on the trained data is extremely high, like the accuracy on the trained data when it comes to classification is high, while the accuracy on the test data set is pretty low. This will mean that the model is not being able to generalize properly on the unseen test data, but it has learned the trained data entirely. And this is a scenario which we will avoid in real life, and such a scenario is called as an overfitting. In summary, the train test split involves partitioning the available labeled data into training and test set. As you can see over here, the model is trained on the larger training set to capture patterns and relationships, while the test set is used to evaluate its performance on the unseen data. The process aids in assessing the model's ability to generalize and make accurate predictions, providing valuable insights for model selection and deployment in real world scenarios. So, having known what this train and test split means till now, we will proceed forward and jump straight into the code and try to understand what we are trying to do in PyTorch and how exactly we can attain this train test split and the evaluation metrics as we had been doing in the past two sessions or the past two videos, when we have incorporated something like a train test split into the model. So yeah, this is how the code looks like. A significant proportion of the code is taken from the previous videos only. For instance, we are loading the EDA libraries over here. We are loading the torch module over here. We use the make blobs from sklearn.datasets, which we used in our video number 2. The only distinct import which we are doing over here is the train test split, and this is a very standard way of splitting the data into train and test sets. And we are going to use the model selection method for sklearn for this task. So we run this, import all the libraries, and over here we will just increase the data size a bit. We are going to have around 4000 samples, and we are going to consider 5 features. Initially we considered 2 features in the previous video, just to make the understanding a bit easy for us, because we needed to see visually how it is looking. So now we consider around 5 features, and this is exactly how the data is going to look like. So it has 5 features. It has target 0 and 1s. So if we just visually look into the target distribution, practically we are not able to see the data and determine a deviation between the two. Like, we can't tell whether a point is actually going to be 0 or 1. That's where we are going to train our deep learning models for. And now if I look into the distribution of the target variable, it's pretty much balanced. Ideally we don't get such balanced data in real life. Just to make the pipeline a bit clear and to make you understand how the train and test validation works, or the train or test split works, we considered a fairly balanced data in our case. The first thing which we will do is to do the train test split, and it's pretty simple. We just call train underscore test underscore split. We pass in the parameter x, we pass in y, we pass in random underscore state, which I'm passing as 13, which is my lucky number, and we specify the size of the test data, which is around 20%. Now it is going to return something. So instead of mugging up what it is going to return, just look, we will look into the documentation to see what it actually returns. So this is the usual format how it should be looking like. So we have to pass in the value of x, which are the set of features. We have to pass in the target as well. We set up a random state so as to ensure that at every iteration of the train test split, if we do it, the results are reproducible. We set up the size of test data to be 20%. It's no hard and fast rule that around 20% of data should be kept as a test set, but ideally I follow this convention. Usually people do the 70-30 split as well in many cases where we really need to use the entirety of data and we don't really want to put so much of data in the validation set. People use 90-10 split as well, but I generally go with the 80-20 split. So now let's look into the documentation to see what exactly it is going to return. Over here we see the documentation. Now it returns something like this: x train, x test, y train, y test. Ideally, if you see this example from the documentation of sklearn, they are using a test size of 33%, which means 67% of data will be used for training and 33% will be used for validation. And the random state is 42, of course, for reproducibility. So I can see that this is exactly the return which we will be getting. Let me copy this and paste it over there. Yeah, we do it. Now we get the train test, y test. So we get a distinct train and test data set completely with labelings done as well. As a first step, we are going to convert the numpy arrays in the form of torch tensors. It's pretty easy over here. So we just do xtrain is equal to torch dot from underscore numpy, and then we write x underscore train. We repeat the same thing for x underscore test as well, and this is the feature set corresponding to the test data. And whenever we see something like train, y underscore train, we do the same thing as we have done before, just that we will be reshaping it. So to reshape it, we use view -1 comma 1, and we apply the same thing for y underscore test as well. So I should make it lowercase over here. Now we can put it as double just to avoid one more line of code, and that's it. And we can check the shape and see what are we getting over here. So basically, the train data is consisting of around 3200 observations, which is pretty much justified because we had 4000 observations and we considered around 80% of it for training. And all these are randomly selected. It's not that the first 3200 observations are taken, these are like 3200 observations randomly taken from the data. And the features is five, like we considered five features uh, corresponding to those 3200 observations. These are 3200 targets which we have considered, and we are going to use it for training. Now these 800 observations are going to be kept reserved as the unseen data which the model hasn't seen in the training phase, and we will see how the model is performing on these 800 data points, which will kind of look like a real world approximation of a data, or an approximation of a real world data which the model has not at all seen. So for that, the first step we will do is to build the class for the model, which is pretty much straightforward. We go with tabular classification, and it has nn dot module as a parent class. We do the initialization, yeah, and then we say self, and there are two parameters, input underscore dimension and output underscore dimension. For this, we have to initialize the parent class as well. Let me copy the name of the function, and then we say self dot init. We do that. We say that we need a fully connected layer, which is nn dot linear. This is the linear activation function which we are talking about. It has an input dimension, output underscore dimension, and we need to find the data type. So this is a very crucial thing. As of now, I am going to write float 64, but just for the sanity check, let me put up a box over here and check the d type of x underscore train to be more precise. So it is torch.float64. We should maintain the same data type over here as well. So we consider torch.float64. Not only of this, let's check the data type corresponding to test as well. It's going to be the same. And similarly, y underscore train dot d type, it's not going to change. Yeah, everything is torch.float64. So we are right in making an assertion that the first layer which we are considering should have a torch.float64 as a data type, and this is the data type corresponding to the weights which we are considering. Now we consider the sigmoid activation function over here, and with that our initialization finishes and we move to the forward layer. It will have x as an input, and things will be pretty much straightforward over here, which will be self dot fcx, and the second output will be self dot sigmoid output, and then we return output. That's it. So on doing so, we are able to uh, set up the class for our model. This is the model class which we are considering. We will proceed in the same way as we did before. So our model is tabular classification, and we are going to pass the inputs. So input dimension is 5 and output dimension is 1. Now how we made such an assertion over here? Now if you look into the shape of the x train, it is 3200 cross 5. So 5 features will be going for each observation, and it will just output one value, which is going to be passed into the sigmoid activation function. So this is how we define the model. We set up a criterion which was nn dot bce loss, binary cross entropy loss, which we are having, and then we set up the optimizer, which is torch dot optim dot sgd model dot parameters, and learning rate we set up as 0.001. Yeah. So now we consider training the model for some finite number of epochs. House it. And now if we look back into our previous videos, we used to apply the model straight away on the x which we used to obtain from here, but we are having two x's over here, two feature sets, x train and x test. So we are just going to train our model on x train, and we are going to validate our model on x test. To do that, it's pretty simple. We say that this is the output, which will be model x underscore train, and the loss will be calculated, which will be criterion, and we consider output dot view minus 1 comma 1, and we consider y underscore train for this task. And there is one small thing which we do: optimizer dot 0 underscore grad, initialize all gradients to 0, and we initialize the backward propagation step as well, and eventually optimizer dot step. So till here, this is a pretty straightforward iteration which we have done, and also we can log the train loss as well, which will be loss dot item over here. So yeah, this is pretty much straightforward over here. Now what we did, we took up the training data which we had, and then we applied a forward pass to it. This is what the forward pass is looking like. So this is like forward pass on train data, and then we calculated the loss over here. We initialized all the gradients to 0, we performed a backward pass and updated all the weights, and we also found out the loss which is happening at this epoch. Now there is an unseen data which is x underscore test, which the model hasn't seen in the entire training phase. Now we have to find out the performance of the model in the training phase after some repeated number of epochs. So we say that if epochs mod 10 is equal to 0, then at this point of time we need to assess the performance of the model. We are going to use model.eval over here. Now let's try to understand what it means. So whenever we use model.eval, it will set the model to the evaluation mode. Previously, it was in a training mode. So this entire thing which was happening over here, the model was in a training mode. Now it is set to evaluation mode. Whenever a model is set to evaluation mode, there are certain behavior of modules which will be different during the training and evaluation. As of now, our code is not having any of these modules because those modules are usually the dropout and batch normalization modules. And what actually happens in that scenario? So whenever we talk about a dropout in deep learning, the dropout layers randomly deactivate a proportion of their inputs to prevent overfitting during the training phase. However, during evaluation and inference, we want the model to use all the features to make the predictions. Now, whenever we are calling model.eval, the dropout layers are going to be disabled and all the units will be active. So this will become much clear when we will be using a lot of dropouts in form of layers in the future networks. But as of now, we are just considering a shallow network and it is not having any dropout over here. So this is how the model evaluation model.eval performs in the case of dropout. So there are some finite proportion of inputs which are deactivated during the training phase, and all this is done to prevent the overfitting. We don't want to deactivate those layers or those proportion of inputs while we are performing an inference. We in fact want all the input features to be present and the model to predict on top of it. So in that scenario, the dropout clause will be stopped in order to make sure the evaluation happens. Similarly, we do something like a batch normalization as well. So the batch normalization uses batch statistics from one layer to another during the training to normalize the input. But during evaluation, the model will typically work on one unit of data instead of, or you can say small batches of data, and the batch size of both the train and test set may not be similar. So we may, in future, if we are building a model, we will be talking about incorporating a batch size as well. So the train batch size may be pretty much different from a validation batch size. So to ensure the consistency and to avoid different statistics during model training and evaluation, model eval will disable the updates of batch statistics. So both the batch normalization and the dropout will be disabled at this step if we do the model.eval over here. Now we move a step further. We are going to use one more thing which is called as a context. So that is, or I should be more specific, it is a context manager. So it is torch dot no underscore grad. Whenever we do this, then something will happen. Let's try to understand what is exactly happening over here. So torch dot no grad is a context manager used to deactivate the gradient calculation and disable the autograd. So we have seen how a computational graph looks like in the past two videos. Uh, the entire computational graph is built inherently in a PyTorch AutoGrad functionality. We don't have to build the computational graph, and with every subsequent backward propagation step in the model training phase, the weights are getting updated. When we are evaluating the model, we are not in the model training phase, and hence we don't need to upgrade the weights periodically. So there is always going to be a forward pass. There is not going to be a backward pass when we are evaluating the model. So when operations are performed within this context, PyTorch doesn't keep any track of the operations of automatic differentiation, which can significantly reduce the memory usage and computation time. So this is the advantage of torch.nograd. There is not going to be a backward pass happening. If only forward pass will be happening over here, and we are going to get the results. So let's type it like this. Output says model x underscore test, and eventually we get the valid underscore loss is equal to criterion x or y underscore, or I should say criterion outputs dot view minus 1 comma 1 comma y underscore test dot item. Now we can say that we can print the train and validation loss at this step. We say that the number of epochs is epochs, and then we say train loss is equal to train underscore loss, and validation loss or the test loss is equal to test underscore loss. So there is a small caveat to the implementation which you can see over here. So we are running the code for a finite number of epochs. Uh, the number of epochs will start from 0. It will go to 1, it will go to 2, it will go to 3, and so on till 10. The moment the number of epochs hits 10, this thing is going to get enforced. And over here, we are considering the model.eval to be at place. It will ensure that the dropout and batch normalization layers are being switched on. And then the torch.nograd happens, which will make sure the back propagation is not happening while we are doing the model evaluation steps. The results are printed and we go to the 11th epoch and the process goes on and on. Let's say hypothetically we had a dropout layer in the first place. So in such a scenario, after the 10th epoch, the model will switch off the dropout altogether. In order to avoid that, a way to do it is to follow a convention where we say that, see, this is the part where we are training the model, and that's what I wrote over here, model.train, and this is the part where we are evaluating the model. So it will become much easy for the model to understand that where exactly it needs to train and where exactly it needs to give the evaluation results. So this is a very important thing. Another thing which we can do is model.train, and we can set up the boolean function to be false, which is equivalent to model.eval. But these things seem to be more convenient. And as of now, even if we don't do the model.train in our code, it won't be affected because we are not considering any dropout layers over here. But in case if you are working on a code where there are a lot of dropout and batch normalization layers involved, it's better to categorically call out the train and evaluation steps so as to make sure that the dropout after a certain point of time is actually being followed and not completely switched off. So now we will run the code and see what results we are getting. So we run it, and this is exactly how we are getting the results. So the train and validation laws are pretty much close to each other. Means if I try to see the history, like from the first set of epochs, the train loss was high, so was the validation loss. Then both the train and validation loss started to reduce. After a particular point of drastic reduction, it came to about 0.27, and it's about 0.22 over here. So it is reduced, and it's also reducing if we increase the number of epochs. But as of now, we can see that the train loss and validation loss are pretty much close to each other. We can also see that the validation loss is pretty much higher than the train loss, a little bit higher than the train loss. In ideal scenarios, we can actually live with it, but if you encounter a significant deviation between the train loss and validation loss, that scenario is going to be called as an overfitting, where the train loss is very less, which will mean that the model is able to understand the train data very much clearly, while the validation loss, which is the loss encountered on an unseen data, if it is high, then the model is not able to generalize well. Our code, which we have written, is kind of able to generalize it, but it could still be improved. And one of the many reasons why this thing has happened, a little bit of overfitting is done, is because of the fact that we are using a shallow network in place. So this was all about understanding how a train and validation split is going to look like. And just to give a brief overview of what all we did, we created the train and test data sets. We saw the features, and we were clearly able to understand that we as human beings can't find any patterns which will segregate the zeros and ones from each other. Moreover, it is a set of 5 features. Visualizing it may be a bit tough. We proceed forward to do a train test split as is shown over here. We followed the documentation and then realized that this is how the train test split looks like. This, all these things which are highlighted are still in arrays. We need to convert it in the form of torch tensors, which we did over here. We looked at the data type because in future iterations it will be needed. We set up our classifier over here, which is having two layers, a linear activation function and a sigmoid activation function. It takes into account two input values, input and output dimensions. The input dimension is 5 because we have 5 features, and output dimension is 1. And we consider the data type as float 64. And we proceed further, and we do the start the model training phase. A bulk of the code which we have written over here from, I think, line number 1 till line number 15 is exactly the same as we have done previously, with the only difference being we are training on the train data, which is like 80% of the 4000 observations which we are having. Now we will be evaluating on the remaining 800 observations, which is the 20% of the observations. So the first step which we did for the evaluation is we switch off the dropout and batch normalization layers. Actually, they weren't even present in our data, but we prefer to use it to make the convention consistent throughout. And then we used a no context manager over here, and it's, if you just hover it, it's clearly shown. that disable the gradient calculation. This is the documentation only. So it is disabling the gradient calculation, and the autograd functionality is being disabled, and we are just doing one forward pass over here. There is no backward pass happening. And then we calculate the validation loss, we print it, and then we realize that our model is able to generalize fairly well on both the train and validation data sets. So that's it for this video. In the next video, we will be discussing few more concepts about torch, specifically in the field of creating a data loaders. Thanks for your time.